Yes, Leah. Okay, let me discuss about the next topic, which is pulse position modulation. Okay. So after discussing sampling theorem, right? Then PAM, as I said, it is a pulse amplitude modulation. So we have discussed what is aperture effect and other things, right? Then we have discussed about the application of sampling theorem, which is TDM, time division multiplexing. Then we have solved some few problems on the sampling theorem, finding the Nyquist rate, and as well as for TDM, finding the minimum bandwidth requirement for transmitting several message signals by using the concept of TDM, and as well as the commutator switch, right? Okay, so let us take up the next one, so which is pulse position modulation. Okay. Okay, so we need to understand why do we go for this PPM? What is the problem in the PAM, right? Pulse amplitude modulation. Only by varying the amplitude of the pulse. So what we are achieving and what were the difficulties in that? To overcome those difficulties, then why do we move on to this PPM, right? Yes, is that fine? Okay, so in pulse modulation system, as I said, we may use the increased bandwidth, okay, consumed by the pulses to obtain the improvement in the noise performance, okay, by representing the sample values of the message signal by some property of the pulse other than the amplitude. Means I said I can vary amplitude of the pulse, or I can vary width of the pulse, and even I can change the position of the pulse, right? I said what is the problem or difficulty only by varying the amplitude of the pulse, right? We have discussed about the aperture effect and all, right? So as what I am saying is, we will be able to increase the improvement in, we can find the improvement in noise performance by representing sample values of the message signal by some property of the pulse other than the amplitude, right? So if I vary the width of the pulse, obviously there will be an requirement of increase in the bandwidth of the system. But with that, we will be able to find the improvement in the noise performance of the system. Okay, so we are compromising with that. So with that, there are two types of things are there here. One is we say pulse duration modulation, and it is also known as pulse width modulation or pulse length modulation. Okay, so these are the three different names. In that, the widely used name is pulse width modulation. Okay, here the samples of the message signal are used to vary the duration of the individual pulses. Okay, I repeat once again, pulse width modulation means what? The width of the pulse is varied in accordance with the message signal, isn't it? So I am using the samples of the message signal to vary the duration of the individual pulses. Okay, so this is known as the pulse width modulation. Fine. So here the modulating signal, okay, may vary the time of occurrence of the leading edge. Okay, that is known as the either the trailing edge or both edges of the pulse. Okay, that is known as the pulse position modulation. Okay, I can use the modulating signal to vary the time of occurrence of the leading edge. Okay, or the trailing edge or both edges of the pulse. Okay, that leads to what? Pulse position modulation. Okay, with the use of these two modulation techniques like pulse width modulation and as well as pulse position modulation, as I said, we will be able to find the improvement in noise performance, right, with the at the cost of what? Increased bandwidth. Hope I am clear. Yes, I am. Okay, now the strength has become 28. It was 8 into 28. Yes, is it clear? Other than Prithvi, anyway, Prithvi will respond. Other people should respond. Even Shreyas will also respond. Akshay will also respond. But others, see this fellow Rushank, even after saying also, he don't say hi. Yes, Anand, Manjunath and all, they are to a certain extent, they are interactive. But some people are there, they never open up their mouth. Yeah, I will ask some question. Okay, with that slide, I think Pooja. Yes, Pooja. Pooja is there? No. What about Nagaveni? Yes, Nagaveni.
Yes, sir.
Yeah. Can you tell what I was discussing? Nagaveni? See, one by one started leaving. Sanket, Sina. Now they have understood I am going to ask questions. Right? Yes, Nagaveni, you can't tell what I was discussing? So what about Leah? Leah? Okay. What about Karunya? Yes, Karunya.
Yes, sir.
Yeah, can you tell me what I was discussing?
Yes, sir. Sir, pulse for position modulation.
Yeah, I was discussing about the concept of pulse position modulation. Fine. I said, yeah, can you just say what I was telling? Karunya.
Pulse pollution,
No.
position
Pulse pollution modulation, huh?
modulation, sir.
Pulse position modulation. Okay, I was discussing about pulse position modulation. Is it possible to say by going to pulse position or pulse width modulation what I'm going to achieve? And what is the drawback in only varying the amplitude of the pulse, that is PAM? You could not get my point.
No, sir.
That is what in first slide only I was there. Okay, please try to concentrate. Otherwise, it won't yield any results. I said by increasing, okay, with the increase of the bandwidth consumed by the pulses, we will be able to find the improvement in noise performance. Okay, by representing the sample values of the message signal by some property of the pulse other than amplitude. What I mean to say, only instead of representing the sample values of the message signal by PAM, right? If I represent that by either pulse width modulation or pulse position modulation, I will be able to find an improvement in the noise performance. But with the use of PPM or PWM, there will be an demand or increase in the bandwidth. Okay, because I'm varying the pulse width, right? So with that, there will be increase in the bandwidth. Okay, but what I can say, there will be an improvement in the noise performance. So that's why I said, so these are the two things. One is pulse width modulation and another is the pulse position modulation. So in case of pulse width modulation, I said the samples of the message signal are used to vary the duration of the individual pulses. Okay, means I have a message signal. then carrier is what? Pulses. So the width of that pulse is varied according to the amplitude of the message signal. That is what the pulse width modulation. Another one is pulse position modulation. Means I will be able to vary the time of occurrence of the leading edge, okay, the trailing edge, or both edges of that pulse. Okay, so depending upon the message signal. Okay, so modulating signal may be used to vary the time of occurrence of the leading edge, the trailing edge, or both edges of the pulse. That is known as the pulse position modulation. Hope clear with this definition. And here these are the waveforms which shows the concept of that. So this is my message signal M of t, and hope clear I feel. This is a message signal M of t, and this one is my carrier signal. So that is the pulses. Okay, I'm using pulse as a carrier. So what I'm finding in the third one is, see, width of this pulse is varied, right, according to the message signal. So here there is a peak, right? So width of the pulse is more, isn't it? So as it goes to the negative, this one, the width of the pulse is small. So this is the waveform of pulse width modulation. Okay, so for positive peak, the width of the pulse is maximum. For negative peak, the width of the pulse is minimum, right? So there will be variations in the width of the pulse. That variation depends on what? The amplitude of the message signal. Okay. Next one is what? The pulse position modulation. Means I can vary the position of this pulse. Okay, position of the pulse. Either it may be a what? Leading edge or trailing edge, or both can be varied, right? So what I'm finding here, see, with respect to this, if you compare, the position of the pulse is changed, right? Isn't it? So for every, means if you all want to understand this ppm with respect to PWM, you have to understand. See, for this negative going, this one now, so there will be a pulse, right? Here I am getting a pulse of certain width, right? So for every negative going, or what we say, it is a trailing edge, right? I get a one pulse. Hope understanding my point, right? So with this, I will be getting one pulse. So it means the position of the pulse is moved, right? Either I can generate for the trailing edge or leading edge. So this is known as the pulse position modulation. Hope this picture is clear. Yes, people should say, is this picture is clear? See, these are the waveforms you are supposed to write. Message signal, a sinusoidal signal, right? Then carrier as pulse. Then you need to draw the pulse width modulated waveform, and then pulse position modulated waveform, that is ppm wave. So in case of PWM, you are supposed to show the variations in the width of this pulse, right? I hope you are able to find the variations in the width of the pulse according to the message signal, right? And here the position of the pulse is varied. This is with respect to PWM, we say. For every trailing edge, I get a pulse. So this is known as the ppm. Even I can generate for every leading edge also. Okay. Yes, is this fine? Shall I go to the next topic? Next slide. Hope noted these things. Yes, I am asking you people only. Have you noted these waveforms? Hello?
Yes, sir. Yes, sir.
Please note down. You are so fast to note down, or you can take the print screen if you are using laptop, right? Shall I go to the next slide then?
Yes, sir.
Okay, so whatever I said in the previous slide, it has been told here in words. I said in case of pulse width modulation, so PDM or pulse duration modulation, right? Both are same. So what happens there? The long pulses, okay, the long pulses expend considerable power during the pulse while bearing no additional information. Okay, that is the drawback of pulse width modulation. Okay, so if this unused power is subtracted from the PDM, that is pulse width modulation, so only time transitions are preserved, right? So we obtain a more efficient type of pulse modulation known as the pulse position modulation. Hope understood this point. In case of pulse width modulation, long pulses expend considerable power during the pulse, okay, while bearing no additional information. Okay, means when it is not carrying any information, it expends a lot of power, right? So if that unused power is subtracted from this pulse width modulation, we will be, means only time transitions are preserved. Time transitions are preserved. Then we obtain what I said, efficient type of pulse modulation known as the pulse position modulation. Okay, so in case of PPM, the position of the pulse, okay, relative to its unmodulated time of occurrence is varied in accordance with the message signal. So that is what is shown in the previous slide here, right? Yes, is this fine? Okay, then yeah. So this is the mathematical analysis of this PPM. So what I'm doing is I'm considering this TS will be the what? Sample duration. Let TS denote the sample duration using the sample M of NTS of the message signal M of T. Okay. What I said? Let TS be the sample duration. Then M of NTS is what? The sample of the message signal M of T. Okay, that is used to modulate the position of the nth pulse. So I can express mathematically the PPM signal as this. So S of T is equal to summation from N is equal to minus infinity to plus infinity G of T minus N into TS minus Kp into M of NTS. Okay, this is fine. So here, what is that Kp? Kp is nothing but the sensitivity of the pulse position modulator. Okay, similar to in PM, right? And as well as FM, we were saying frequency sensitivity and phase sensitivity, right? So similar to that, here we say Kp is the sensitivity of the PPM. Okay, and G of T denotes the standard pulse. Okay. So G of T minus N into Ts, right, minus Kp into M of N into Ts. That will be the our PPM signal. Okay. So the different pulses constituting the PPM signal S of T must be strictly non-overlapping, right? So sufficient condition for this requirement is what it has to satisfy. This G of T will be equal to 0 when T is greater than Ts by 2 minus Kp into the maximum value of M of T. Okay, so it has to satisfy that condition. So Ts by 2 minus Kp, that is a sensitivity of the PPM into the maximum value of M of T. So in turn, which requires, means Kp into M of T should be less than or equal to less than Ts by 2. Okay, so what we are finding here by observing this equation is this Kp into M of T maximum, right, is to 1/2, right, 1/2 the sampling duration, right, because it is Ts by 2, right? So this Kp into M of T maximum should be less than Ts by 2. Means what? Is one of the sampling duration, the narrower must be the standard pulse. Means the width of the pulse should be less than this. Means half of the sampling duration. Okay. So in order to ensure that the individual pulses of the PPM signal do not interfere with each other. Okay. Fine. And the wider will the bandwidth occupied by the PPM signal, right? So this equation 7.21 is satisfied, and that there is no interference between the adjacent pulses of the PPM signal. Okay. Then the samples M of NTS can be recovered properly if this condition is satisfied. Okay. So if the message signal is strictly band limited, then it follows from the sampling theorem that the original message signal M of t can be recovered from the ppm signal S of t without any distortion. Okay, so I will explain this with the waveform. So then I think this picture will be clear. Okay. So first of all, we should be able to understand how do we represent the ppm signal mathematically. Okay. So S of t is equal to this. So G of t is the pulse. So we are going to vary the position of that pulse, and sum of all those pulses will give you the ppm signal, right? So G of t minus n into ts minus ap into m of nts. Let me say the block diagram of ppm. Okay. First, let me say with respect to block diagram, and then let me take up the waveforms. So the first thing is we need to feed the message signal to the sample and hold circuit. Hope you all will be able to visualize what is the sample and hold circuit. So there will be, I think, I will show the circuit of the sample and hold circuit also. Okay. So two switches means I need a switch and as well as a capacitor to hold that value, right? So when the switch is closed, it will be taking the sample of that message signal. So capacitor can store that value. So that is why it is called sample and hold circuit. Okay. I will go to that circuit only right now. Okay. How does this works? Then I will come back to that. Yeah. So this is what the sample and hold circuit. Okay. So I will be feeding the analog input signal here. So here there will be a switch, right? So when the switch is closed, it is taking the sample of this analog signal. So capacitor will store that value. Okay. So when the switch is open, then capacitor will discharge. Right. So this is very simple circuit. The first one, just to understand, here we give analog input and we get the analog output only. Right. So even to understand better way, like we can refer this circuit. See here G1 and G2 are there. It means we have two switches, right? One is connected in series, another one is connected in parallel across the capacitor. So here for these means at the gate of these switches, we will be applying a clock pulses. Okay. So when the sampling switch is closed, means I need to apply a clock here, right? So when the clock is high, the sampling switch will be closed. So it will take the sample of this input signal, right? And during that time, this G2 switch will be open. Okay. When G1 is closed, G2 will be open. And when G1 is open, G2 will be closed. So that's mechanism you understand. Okay. So this we call it as a sampling switch, G1. And G2 we call it as a discharge switch, right? So when the sampling switch is closed, means it takes the sample from the analog input signal. So the capacitor will be charged to the peak voltage, right? So if I consider this point, so it holds that value, isn't it? It charges to the peak voltage and then it holds that value. Okay. Then what happens when the voltage is across the capacitor, right, is less than the analog input signal? What happens then? This G2 will be made on. Okay. So during that time it will be discharging, right? So that process repeats. And I think yeah, you will be able to get this signal. So this is my analog input signal X of t, right? And this is my rectangular pulses, G of t is pulse, right? And this is my flat of samples. This is about the flat of sample, right? So this is what the sample and hold circuit is. Means I get a PAM signal at the output of the sample and hold circuit. That is the first stage. Okay. To get the PAM signal, we use the sample and hold circuit. Yeah. So that is why we say here pulse generator, right? So pulse generator is one input to the sample and hold circuit. Another input is our message signal. Okay. So internal block diagram, circuit diagram, I have shown how it will be. Then I get here what PAM signal. Okay. That will be added with the sawtooth generator. Okay. From pulse generator only, I can get here the pulses at this point like this. Then even from the pulse generator, I can get the sawtooth wave also. So those two will be added. Okay, PM signal plus sawtooth waveform, both will be added. Then that will be given to the threshold detector. Okay, so depending upon the threshold value, right? I get the impulses. Okay. Then by using a pulse shaping filter, I will be able to get the ppm signal. Okay, so this is what in a nutshell the block diagram of the ppm waveform generator. So input signal, that is a message signal, will be one input of the sample and hold circuit. Another input is what? The pulses from the pulse generator. Then output of the sample and hold circuit is a what? PM signal. Okay, that will be added with the sawtooth generator. Then that will be given as input to the threshold detector. Okay, so depending upon the threshold value, so this output of this threshold detector will be a pulses. Okay, so and then that will be given as input to the pulse shaping filter to get the proper ppm signal. So I will show you the waveforms. How does this happens here? So this is the first part, just the message signal, right? And then this is my output of the sample and hold circuit. Okay. So these two waveforms. Then after that, after PAM, what I said, that will be added to the sawtooth waveform generator, right? So I think I will show that waveforms only. Yeah. So this is my sawtooth waveform. After adding, it becomes like this. Okay. So here, if I take this is my threshold value, right? Then for every negative going this one, right? When the value goes below this value, I get a pulse. Hope you are able to understand this. For every negative going means when this sawtooth waveform goes this below the threshold value, I get a pulse here, right? Even for this also. At this point you think, then at this point, right? This point. Similarly, this point. Okay. Yes. So these are my I of t, means pulses. If I pass these signals through a pulse shaping filter, I get the proper ppm wave. Okay. Yeah. I will show another waveform where the still picture is clear. Yeah. Hope we'll be able to understand this, right? So this is my what PM signal. Okay, that will be added with my sawtooth waveform. Okay, this is a sawtooth waveform, right? So first I get don't means output of the comparator as the PWM waveform. Then I said for every means whenever it goes below this threshold value, no, I get a position pulse, right? It is written very clearly. For every negative going this one, I get a pulse. So this is my ppm output. Yeah, so other way of representing is first you draw the waveform of message signal. Okay, then this is my pulses as a carrier, then this is my PWM wave, and this will be my ppm wave. Okay. Yeah, so I was telling the message signal will be given as input to the sample and hold circuit, right? So that sample and hold circuit, I said it will convert that input message signal into a PAM signal, right? By means of sample and hold. Right, then the pulse duration T of the sample and hold circuit will be the same as the sampling duration Ts. Okay, so after that, the output of the sample and hold circuit is added with the sawtooth waveform. So that will yield the combined signal V of t. So which is shown in the block diagram, right? Then that combined signal V of t is applied to what? To the threshold detector, right? So that will produce a very narrow pulses, so which is approximately or approximating an impulse, right? Each time V of t, I said crosses the zero reference line, then I get a negative going direction. Okay. Each time V of t crosses 0 in the negative going direction, I will be able to find a sequence of impulses, right, which is generated. That is known as the ppm signal. Okay. Then I said those sequence of impulses will be given to the pulse shaping filter to get the standard pulse position waveforms, okay, or standard ppm waveforms. Yeah, so this is all about the generation of ppm wave. Okay, so hope the things are clear. So this is a block diagram, as I said, right? It will have sample and hold circuit. I said one input to the sample and hold circuit is your analog message signal. Another input is the what? Pulses, right? As a carrier. So output of that sample and hold circuit is a PAM signal. Then I add that PAM signal with the sawtooth waveform, right? Then that will be given to the threshold detector, right? So then I will be able to create the series of impulses. The output of the threshold detector will be given to the pulse shaping filter to get the proper ppm waveform. Yeah. So then let us try to understand how do we do the detection of ppm wave. So that is at the transmitter side, right? So at the receiver side, we need to again do the reverse process, right? So to do that, there are different ways to do that. So we will be discussing here two ways. Okay. So to convert the received ppm wave into the first way is that we convert that ppm wave, received ppm wave into pulse width modulated wave, a PDM wave with the same modulation. Then we integrate this PWM wave using a device with finite integration time. Okay, means integrate and dump circuit you might have heard. Okay, so by using that, we will be able to compute the area under each pulse, okay, of the pulse width modulated wave by doing that integration, right? Then sample the output of that integrator at a uniform rate, okay, to produce the PAM wave, right? So whose pulse amplitude will be proportional to the signal samples, that is M of NTS of the original ppm wave S of t. Okay. So I repeat once again, to detect ppm wave, what we do is first we convert the received ppm wave into PWM wave. Okay. Then we do the integration of this PWM wave using a device which is having a finite integration of time, right? So with that, we will be able to compute the area under that pulse, right, of the PWM wave. Then we do the sample, okay, the output of that integrator at uniform rate to get back the PAM wave, right? And the pulse amplitude of that will be proportional to the signal samples of M of NTS of the original ppm wave S of t. So this is one way. Okay, other way is means after getting that, okay, PM wave to recover the message signal M of t is we need to do the demodulation, right? Demodulate the PM wave to recover the message signal M of t. Hope clear? So input is ppm. From ppm we get PWM. Okay. Then that PWM waveform will be integrated by using a integrator, right? Then we convert that PWM wave into a PAM wave. Then we do the demodulation to get back the original message signal. So it is entirely exactly the reverse process what we have discussed in the transmitter side. Okay, so this the practical ppm receiver will have a nonlinear device. Okay, so those nonlinear devices are known as slicer. Okay, I said the practical ppm receiver will have a nonlinear device called the slicer at its input end. Okay, so let us see what is the function of that slicer and what is its input output characteristics also. So here this diagram shows the input-output relations of the slicer. Okay, so what you are finding here, x-axis is the input and y-axis is the output, and this is the slicing level. Okay, so the slicing level is normally set at approximately half the peak pulse amplitude of the received ppm wave. Okay, half of the peak amplitude of the received ppm wave, that will be the slicing level, okay, set at the slicer. Okay, so this is the slicing level, right? Here I have written shown slicing level. So the value of this will be what? Half of the amplitude of the ppm wave. Okay. So what this slicer will do? Okay, the function of the slicer is to preserve the positions of the edges of the received pulses. Okay, and remove everything else. Because when we transmit a signal over the air or through the wire, what happens? The noise will be added. We all know in the channel the noise will be added, right? So because of that, what happens? There are chances of changing the position of the pulse, right? So to overcome that problem, we use the slicer, right? What the slicer will do? It will preserve the positions of the edges of the received pulses and will remove everything else. So by doing so, means it will be producing a rectangular pulses, okay, which are fairly sharp leading and trailing edges, right, at the same instance as the corresponding edges of the received pulses. Okay, so the output of the slicer will be a rectangular pulse, right? It will have sharp leading and trailing edges, and those leading and trailing edges will be at what instance of time? It will be at the same instance of the corresponding edges of the received ppm wave, right? So in a loose sense, what I can say is the slicer acts as a noise cleaning device. Hope you understand what I'm saying. The slicer acts as a noise cleaning device. Okay, so the final noise level at the output of the receiver is greatly reduced by eliminating all the noise in the received ppm wave except in the neighborhood of the leading and trailing edges. Okay, because the slicer will be producing a rectangular pulse with sharp leading and trailing edges, right? Those instants of time will be same as that of the received ppm wave. So it will be cleaning the noise. But near to that, okay, that is the neighborhood of the leading or trailing edge, there will be some amount of noise. So that will be there as usual. Okay, but exactly at the leading and trailing edges, if there is any noise, that will be eliminated by the slicer. And this is the pictorial representation of that. Okay, so detection of a noiseless ppm signal. So first one is the what? This is the nth pulse of the ppm signal, right? Hope you understand this. See, this is NTS. This is M of NTS is written from here to where, and this will be the slicing level, right? Hope you are understanding what I'm saying here. The slicing level. For it, every slicing level, I get a pulse. So this is the output of the slicer, right? So I get a sharp impulse function, right? And that will be delayed version of the slicer output. So this is if I think this is del of t, then this will be del of t minus NTS minus m into NTS, right? Then this is what? The pulse width modulated wave. Okay. So the output of the slicer is differentiated and then half-wave rectified to yield the very short pulse. Okay, as I said, which is approximating an impulse each time the amplitude of the pulse in the received ppm wave, okay, which passes through the slicing level. Okay, so after converting the received noisy ppm wave into the pulse width modulated wave, okay, with the same modulation, as I said, we will be the receiver then proceeds to reconstruct the original signal the original baseband signal M of t in the same manner what we have discussed earlier. Okay. Means it will be converting into PAM, then from PAM will be getting back the original message signal. Just hope this point is clear. The function of slicer, how does it eliminates the noise at the leading and trailing edge of the PPM wave at the receiver side, and why it is required, right? Yeah. So I repeat once again what I said to detect the PPM wave, right? First, what we do, we convert the received PPM wave into PWM wave. Okay, then we do the integration, right? Which is having a finite integration time. So with that, we will be able to compute the area under each pulse of the PWM wave. Then we do the sample, right? The output of, we do the sampling of the output of the integrator at a uniform rate to produce the PM wave, right? And it means the output of the PM wave, its amplitude is proportional to the signal samples of the original PPM wave, right? Then we do the demodulation of the PM wave to recover the message signal. So this is one way, right? I said, and I said in practical PPM receiver, we use a nonlinear device known as the slicer at the input of the receiver, right? I have shown what is the input output characteristics of the slicer, right? Then I said, how do we set the slicing level? Okay, the slicing level will be equal to what? It will be approximately half of the peak pulse amplitude of the received PPM wave, right? So what this slicer will do, it will be preserving the positions of the edges of the received pulses, okay, by removing any other noise. So means slicer will be producing a rectangular pulse with sharp leading and trailing edges at the same instance corresponding to the edges of the received PPM pulse, right? So what I can say is slicer will act as a noise cleaning device. Okay. So the final noise level at the output of the receiver has been reduced to the great extent by eliminating all the noise in the received PPM wave except the noise which is there in the neighborhood of the leading and trailing edges. Okay. So this is what the pictorial representation of that, whatever I said about the slicer, output of the slicer, and then how do I get that, right? Yeah, so output of the slicer will be differentiated, then it will be half-wave rectified to yield very short pulses, right? So each time the amplitude of the pulse in the received PPM wave passes through the slicing level. So I think, yeah, which I have shown in the previous diagram, I think. Yeah, how do we get that sharp pulses? Yeah, this one, I of t. Okay. Yeah, let us try to understand about the noise in pulse position modulation. Okay. So in PPM system, the transmitted information will be contained in the relative positions of the modulated pulses, right? That's why it is called pulse position modulation. In case of PWM, the information will be contained in the width of the pulse, right? In case of pulse amplitude modulation, the information is contained in the amplitude of the pulse, right? So I hope you are able to understand these three different pulse modulation techniques: PAM, PWM, and PPM, right? So information is contained in the amplitude of the pulse in case of PAM, and information is contained in the width of the pulse in case of PWM, and information is contained in the position of the pulse in case of ppm, right? So the presence of additive noise, okay, the presence of additive noise, as I said in the channel, usually we assume it is an additive white Gaussian noise, right? So the presence of that additive noise will affect the performance of the system. Okay, how does it affect the performance of the system? By falsifying the time at which the modulated pulses will judge to occur, means the trailing edge or leading edge, right? With the noise added to that, we may take a decision about the trailing edge or leading edge at wrong times, right? So because of the noise. So immunity to noise can be established by making the pulse build up so rapidly that the time interval during which the noise can exert any perturbations in a very short. Okay. So what we do that, we develop an immunity to noise. Okay, established by making what, a pulse, right? Means we are going to establish by making a pulse build up so rapidly that the time interval during which the noise can exert any perturbations in a very short, right? Means the additive noise would have no effect on the pulse positions, okay, if the received pulses were perfectly rectangular, okay, because the presence of noise introduces only the vertical perturbations. Hope understanding my point, what I'm saying. To understand what is the noise in ppm, I'm discussing about this, okay. So however, the reception of perfectly rectangular pulses, okay, so that is why here comes into the picture of that sinc function. As I already said, what is the Fourier transform of a rectangular pulse? It is a sinc function, right? Similarly, if the sinc function in time domain, its Fourier transform will be a rectangular pulse. So we have observed is, if I use a rectangular pulse, in case of frequency domain, what it requires infinite bandwidth, right? But it is practically impossible to have an infinite channel bandwidth, right? In reality, right? So that's what I'm saying here. So the reception of perfectly rectangular pulses implies an infinite channel bandwidth, which is impractical in reality, right? Fine. Then what is this one? So with the finite channel bandwidth, in practice, what we find is the received pulses will have a finite rise time. Okay. I hope means it will not be like this, right? It will not be a sharp rectangular pulse. Even it may take some time. Means you may have understood like this, right? This is a rise time, right? Then similarly, there will be a fall time also. So this we call as a rise time, and this we call as a fall time. So the received pulses will have finite rise time, so that the performance of the ppm receiver will not be affected by noise much. Okay. So with the continuous wave modulation, the noise performance of ppm may be described in terms of output SNR. I think this already we are aware, right? How do we measure the performance of any system, any communication system, right? We take output SNR, then we take input SNR. The ratio of that will give the figure of merit, and even channel SNR also, right? Okay. So to find the noise improvement produced by the ppm over the baseband transmission of the message signal, so we are using the figure of merit, right? So defined as the output signal to noise ratio of the ppm system divided by the channel signal to noise ratio. Yes or no? I hope this already we have discussed in case of AM, FM and other things, right? And we have derived also what is the expression for the figure of merit for AM and figure of merit for DSBSC modulation and the figure of merit for the FM, right? So with that, we will be able to say what is the performance of the improvement of noise or performance of the system over noise of that particular modulation technique. Yeah. Yeah, this is all about the detection of, I think, noise in the ppm. Okay. Hope, I think with this, what I can say is this module is completed. Okay. I think I have given a quiz. You people can take up that quiz. Okay. It's because so far I have not given any quiz or assignment. We can take that, complete in time. If you have any questions to ask, you can ask related to ppm generation and as well as the detection. If you don't have any questions, so then I will ask questions from my side. You have understood everything. Yes, no questions. Aditi.
Sir,
Ah,
sir,
yeah, tell me
the
Akshay.
slicer part,
Huh?
slicer,
Ah, slicer, yeah.
it is not a procedure like it is not a procedure of detection, no, sir. It is just an application.
Ah, not the application. It will be one part of, means as a building block in the receiver. I
Yes,
said no, it will be eliminating the noise at the trailing and leading edge of the ppm wave.
yes, sir.
Of course, it is, I think while showing block diagram, it is not shown in the block diagram as a slicer block, but it is there at the input side. Yeah, receiver block diagram when you have not written. Right? Just I am telling the process. How does it happen? So I said now this slicer will be used at the input of the receiver, ppm receiver, because it plays a key role in eliminating or minimizing the noise.
Yes, sir.
Yeah. So any other questions? Anand?
No, sir.
No. So everything is understood. Hmm?
Yes, sir.
Okay. So can you just tell in your own words, how do we generate ppm wave with your understanding?
Sir,
Yeah.
first the message signal is sent to the sample and hold circuit, sir.
Okay. So what will be the
Where
output of the sample and hold circuit?
U of t will be the output, sir.
No, means is it a PAM wave or PPM wave or a PWM wave?
Sir, PAM, sir.
PAM, right? So output of the sample and hold circuit is a PAM wave. Okay.
Yeah.
Then what we do?
Then it will be sent to the adder, sir.
Uh,
Uh,
so what do we
where
add here?
uh, pulse.
Yeah, PAM wave will be added with the sawtooth waveform, isn't it?
Yes, sir.
Uh, then output of that will be given to the threshold detector, right? So whenever the output of this adder goes below the threshold value, right? For every means we get a pulse, right?
Yes, sir.
Means with respect to PWM wave, for every uh, trailing edge, we get one pulse.
One pulse. Yes, sir.
Uh,
Uh,
then
uh, then then finally ppm signal is generated uh, using the filter circuit, sir.
okay, so for shaping the pulse, we are passing it through a pulse shaping filter.
Pulse shape
Okay,
filter.
fine. What about Ananta? Ananta? Yes, Ananta.
Yes, sir.
Hmm. Can you just brief about the detection of ppm wave? Detection of ppm wave, man. How do we do that? What is the first step? Ananta, I think you are not concentrated.
Sir, I have some network lag, sir. I can't see the screen properly.
Then you would have told me, na.
So now it's happening, sir. I'm seeing something black.
See the first step is we convert ppm wave into PWM wave. Okay. After
Yeah.
converting that ppm wave into PWM wave, we apply that to the integrator circuit. Okay. So we do the integration of that pulse to find the area under each pulse. Okay. So after doing that, we do the sampling of that integrator. We get the PAM wave. Okay. After PAM, we do the demodulation to get back the original message signal. So this is what the process of getting back the original message signal from the ppm received signal. Okay.
Yes, sir.
Yeah. Yes, sir. Chandana.
Yes, sir.
Can you tell the importance of slicer circuit, the ppm receiver? What it will do, slicer circuit?
Sir, it halves the peak pulse amplitudes.
Pardon? Yeah, can you repeat once again, Chandana? I could not hear.
It halves the peak pulse amplitude, sir, of the receiver ppm.
It halves up. I said the slicer circuit acts as a means that is a slicing level. Okay, the slicing level is set at what? Half the peak amplitude of the ppm wave. That is a slicing level. But what is its function? I said that, yeah.
Preserve the position of the edges, sir.
It will preserve the positions of the edges of the received pulses. So with that, what I can say is it produces the rectangular pulses, okay, with the sharp leading and trailing edges at the same instance, which corresponds to the edges of the received ppm wave. So with that, what I can say is this slicer acts as a noise cleaning device. Okay, so at least at the edges of the ppm wave, it will be cleaning the noise, but there will be some amount of noise near the leading and trailing edges. Okay, so that will not be able to clean up by this slicer circuit. Exactly at the position of trailing and leading edge, it will be able to eliminate the noise. Okay. So, okay, with this, I will stop today. As I said, completed, I can say this module 4 is completed.